Welcome to today's Webcast series presentation, The Value of Intelligent 3D Bridge BIM in Transportation Projects. My name is Bob Drake, editor of Civil and Structural Engineer magazine, published by Zweig Group, and I will moderate today's session. So thank you for joining us for this webcast, which is sponsored by Bentley Systems Incorporated. The views of the speakers and organizations participating in this webcast are their own and do not necessarily reflect those of Civil and Structural Engineer or its publisher, Zweig Group. If you have any technical difficulties while viewing this webcast, please submit questions or a brief explanation of your technical problem using the Ask a Question box on the left side of the webcast dashboard, and a representative will assist you. Note the button in the upper right corner to enlarge the slide viewing window if desired. During the webcast, you also can submit questions to our speakers using the same Ask a Question box. Submit your questions at any time, and we will try to answer as many as we can later in the webcast. Zweig Group encourages group learning for our events. If you're viewing the live webcast with a group on one registered person's computer, that person must complete and submit the multiple viewer registration form for the group in order for everyone to earn credit. To download the multiple viewer registration form from the event resources on the left side of the webcast dashboard. Submission instructions are on the form. Also note a link in the Event Resources section to download a PDF of the slides in today's webcast. Additionally, at the end of today's event, we'll provide a webcast evaluation survey for you to submit your feedback. Today's presenters are Raul Amaya, Senior Application Engineer with Bentley Systems, Andre Toussaint, Virtual Construction Engineer, PCL Construction Services, and Dennis Fontenot, Regional Technical and BIM Manager, Commercial Metals Company in the Central Region. The learning objectives for the event are shown for your review. Details on downloading a certificate of completion will be provided later in the webcast. Viewers of archived webcasts must pass a quiz in order to download a certificate of completion. So let's get started. Raul, I hand it over to you.
Thank you, Bob. And again, thank you for attending this webinar. One of the first things that I wanted to mention to you is interoperability. This is a powerful word. How can we take one model and relate to civil data, change alignments, the model is supposed to change? What about the DTM? If you have it, can we use it to calculate automatically the top elevation of the footing, for example? It's powerful, right? But interoperability is only really possible if we work on the common data environment. Here is the key to success. How can we utilize data and share that data throughout the process of the project without copying, without translating, without modifications? That is, to me, the key, again, to success. Now, three things: the what, the how, and the why. I like these three words. I love this. Is my manager have really imprinted this into my mind. What are your issues that you have? Okay, that is something that we hear all the time. How we can actually help you and give you the solutions to minimize these issues that you're having. And why? Let me tell you how we're going to do this. First of all, believe me, all of us in the webcast today have lots of issues. I know we heard about them in many locations that we visit. Okay, these are some of them. Okay. You can create models, right? Everybody tells us that, but they are not connected to civil data. Or, for example, the DTM, okay, it's available, but how can we utilize it? Analytical solutions, the model that I actually am working with, all the way from civil data, preliminary, or alternative solutions, how can I connect to analytical solutions? Constructability alternatives, for example, I would like to have as many constructability alternatives. I would like to know cost, interferences. What would happen? That question is very common. Now, But this is how we're going to help you, okay? All models are integrated with civil data. You change the alignment, the bridge will react. You change the profile, we'll react to that. The DTN models, we can now utilize it to calculate, the top of the footing elevation. And if you move the pier to a different station, guess what? Those elevations will be recalculated, okay? Models can now be connected to analytical solutions. The same model, remember that. This is very important. I don't have to do anything additionally in order to go to the analytical solutions. Constructability, the sections, if I'm doing, for example, pro concrete to add reinforcement, yes, I can add, but I'm not copying. I'm relying on that same model in order to give that boundary in order to add the reinforcement, okay? And the why. Why? Because, believe me, every time that you work in this common data environment, you save time, it's money, cost savings, right? Accelerated deliverable. This is very important. Now I can accelerate without sacrificing anything, okay? Which will reduce the risk of errors, omissions. What about revisions? Every time that we do a revision, that costs money, okay? Increasing quality, that is important. Okay, so guess what? If we can look at this slide right here, you look at that capture that I did, is all related to the terrain. Everything that you see there is exactly the project. That's the work that I'm doing. Did I check interferences? All of these things, all the issues that we're discussing. You know what? This is a long model, but easy to use, really. Very easy to model with OpenBridge Modeler. Well, it can be complex, okay? If it is complex, it still is easy to model. And this is important, okay? Because how can we do a model of bridges with simple components as you see here? They're very simple, right? But OpenBridge Modeler is working on a common data environment that allows us to simply provide information and let OpenBridge Modeler do the rest, okay? In this case, piers can be standards, multi-column, circular, rectangular, wall piers, but also look at the other variations that makes it this beautiful. Now, going to analysis. The same model that I'm actually creating is intelligent, okay? I can transfer that to analysis, either RM bridge to do complex, or lead bridge concrete, or lead bridge steel, okay? Or utilizing the same model, though. That is very important, okay? I'm using the same model to be able to add the 3D reinforcement. I can do class detection, scheduling, detailing. Later on, you will see that in another presentations, okay, today. All right, so once again, to summarize the what, the how, and the why, okay? Don't forget that. That's very important, and how we can help you with that, okay? And why is only to help you increase your productivity. All right, so what I'm going to do next is that I'm going to show you a video, okay? And in this video is going to simply show you how we model the structures and how we go to analysis and we create a little bit some of that, okay? I want to show you how now utilizing OpenBridge Modeler, working in a complex project like this, how we model bridges. In this case, what we're going to do is a segmental bridge span by span with minimum information like typical segment length, pier segment length, and so on. The only thing we need to do is to select the unit. We can support multiple units. So what happens is that automatically OpenBridge Modeler is going to calculate for example, in this case, the closure joint length. We don't have to define them. This is automatically calculated. If I expand the tree, we can see that I have an alignment and also a terrain model. That eventually I will utilize that to place my piers. In this case, I'm going to view one of the spans. I have 17 segments in that particular span. But if I change that segment from 4 to 4.5 meters, what would happen? Okay, so automatically the bridge is calculated. Will give us a completely different number of segments, And this is important for the contractor, right? You want to accelerate construction, and this is one way of doing it. What I'm going to place next is the substructure, some piers. I select a template from the library and select multiple locations where I want to place that pier. Automatically, that pier is going to be placed. The top of the pier will be relative to the superstructure. The top of the footing will be relative to the DTM. This happens automatically. If you move the pier, the height of the pier automatically changes accordingly, depending upon the DTM. In this case, if I select the pier and I look at its properties, I will be able to go to the constraints and make changes. In this case, at the top of the footing, I want it to be at -1 meter below the DTM. I apply and notice that automatically the pier is extended. Later on you will see that this is available when you are working with other disciplines downstream. In this case, I want to look at the quantities, and this is important because you can have different alternatives, calculate the quantities automatically for whatever alternative that you're working with. In this case, you can also create input, what you did, deck elevations, etc. In this case, what I'm going to do is to place an straddle bend at the location of the intersection of bridge 18 and 19. Okay, very simple. Again, you select the pier line and the straddle bend is placed. Once again, the top of the pier is based on the superstructure and the top of the footing based on the DTM. Okay, the next example that I want to share with you is a cantilever, precast cantilever construction. What you see here is a bridge that has a custom height. This is the section that, utilizing dynamic views, is shown. I have already placed a bearing below. Beautiful thing is that the top of the pier is automatically adjusted. No? I'm going to do that here. I'm going to place a bearing. So what I'm going to do is go to the place bearing tool and select the type of bearing that I want to place on the next pier. And again, you can do this in all of the piers if you want to automatically. Okay. In this case for today, then I'm going to select a cell. Okay. Different ways of doing it, different options. In this case, DS Brown type, I select the pier line very nicely. I reset, and the bearing is placed and automatically adjust the top of the pier. Very nice, very easy, very easy. Alright, so next, what I'm going to do is the constraints. I want to change the height of this pier to vary it at the supports, parabolically. So this is the height, and this is the constraint, and I want to add to this table how this bridge will vary it longitudinally. So I do that and notice that I have all kinds of options: parabolic, star, linear, curvy, you name it. Okay, so that's simple. So now, as soon as I apply this variation, what's going to happen that the height of the bridge is going to vary. Okay, including the bearing. Remember the bearing that I had placed? It will going to be pushed down. The top of the pier will be moved down accordingly. Very nice, very easy, very quick. Now, going to the interoperability, that's beautiful because I'm using one single model to do many things. In this case, I'm going to go to RM Bridge to do the analysis, time dependency. I add tendons. I will add all the low cases, whatever is necessary for the application. In this case, segmental. You can see the tendons that I have added. You can see the schedule stage simulation that I defined in OpenBridge Modeler. Over here, we can see the substructure being placed first, and then how the cantilevers are going to be constructed, etc. Okay, I'm going to exit RM Bridge. I'm going to go back to the OpenBridge Modeler. What I'm going to do is something amazing. I'm going to take this straight bridge and I'm going to change it to another alignment. Okay, and this is what it takes. Simple, very simple. because we are sharing the data. Working on a common data environment allows me to do this, what you see here. Okay, very easy, and we are the only ones actually doing this, working in a true common data environment that permits us to do many changes very easy. Okay, so then again, I'm going to go back to RM Bridge. Okay, so I'm going to connect this model with RM Bridge, and what I expect is that previous model that you saw is going to change accordingly. Okay, we don't lose any information in the model. You can make adjustments, but we don't lose any previous defined information, as you can see here very nicely. Okay, now one of the things I'm going to do is to take this model, and I want to say the tendons because I want to view them in OpenBridge Modeler. Okay, the reason being is that I'm going to take this model, the same model that I started from the preliminary, that if I change the alignment, the bridge moves, it changes the profile, the bridge moves. Well, I want to take now to ProConcrete, okay? And therefore, that's the reason why I want to bring the tendons into the model itself, so that when we add reinforcement, now we are aware of clutch detections and things like that. Later on, you will see other presentations related to RM itself, ProStructures, ProConcrete, okay? So now what I'm going to do is take the typical segments, okay, and I'm going to turn them off. I'm going to go to the element information and visualize what I brought from RM Bridge. Okay, so if I expand the tree of the tendon properties, you will see now areas and what that tendon is made of. Okay, so I'm going to go simply back now and take this model and bring it into as a reference file. I'm not going to copy the model. I'm going to reference into a ProStructures ProConcrete DGN file for rebar. So what you see here is the original model, okay, the one that is straight. So I have some already reinforcement in there, as you can see here, and then all of a sudden, what I'm doing is taking this model and reinforce it. Now, since it's a reference file, I want to bring it and simply reload the model that I have modified from a straight alignment to a curve alignment. Okay, and guess what happened to the pier that I have there with reinforcement? It will be updated, it will be relocated, it will be forced to follow the new changes. Okay, well, you know, just to finalize, I'm almost at the end of this particular presentation. So I want to add rebar to the footing. And remember, the scheduling and drawings and everything that we generate from this model are the actual sections that came from the OpenBridge Modeler to begin with. Advantages of really working on a common data environment. Thank you. Okay, so thank you very much. Now what I'm going to transfer the presentation to Andre. He's going to be covering the 3D models and bridge construction, a contractor's perspective. Andre, are you ready?
Yep. Thanks, Raul. So, as mentioned earlier, my name is Andre Tusingout. I'm a virtual construction engineer with PCL Construction Services in Orlando, Florida. And I wanted to give everyone a little bit of a flavor of how, as a contractor, we use 3D engineered models and building information modeling from our standpoint. So, briefly, just about PCL, we've been building for over 100 years. We've grown to one of the largest general contractors in North America. And in terms of BIM, our view of things is really that you can't view it as just a software or just a tool, but it's really a combination of tools, processes, and behaviors to go ahead and make your project a success. So PCL, we are primarily a buildings contractor. We do traditionally a lot of systems coordination. Seen here at, this was the San Diego airport. We use a lot of Revit. We use a lot of building information modeling because we are a self-perform concrete contractor. So we do a lot of self-perform lift drawings for quantity tracking and planning. On the infrastructure side, especially once you get into some of the complex pursuits, as shown here, we really find BIM useful, especially on the 4D and clash detection standpoint, which I'll get into a little bit further. And then also from, say, just a general erection and concept conveyance standpoint. This here, I kind of call this Hollywood BIM. This is really one of the fancier images that we've kind of generated out of the models that we actually use to plan and execute our work. Let's see. So the very first job I just wanted to go through as an example, this was actually a pretty small job. It was an accelerated bridge construction job in Hartford, Vermont. What you see here, this is actually a model of the existing bridge that we did in LEAP steel. We combined it with point cloud scan to the existing bridge, and this was done during the pursuit phase. So it was really important for us, anytime we're in pursuits or we're design builds, that we have models that can kind of be flexible and that are parametric, so we're not redoing work. We're actually saving time. We're not just generating a 3D model for the sake of having one. In the case here at Hartford, we actually took this model, pushed it downstream. This is actually Synchro. We did a whole 4D schedule on this. We were able to take a lot of the data from VTrans, from Inroads, DGN, a number of other formats. We took our temporary works designs and we pushed it all into here this 4D schedule, because this particular job, being accelerated bridge construction, we had 2 weekends to slide the existing bridges, demo the existing bridges and slide the new bridges into place. And when you have a tight timeline such as this, having a tool that allows you to really plan and view everything and view those conflicts and vet them out beforehand is really critical. From a steel bridge standpoint, this is the Gilmerton Lift Bridge in Chesapeake, Virginia. From a structural steel, this was pretty complicated. There was over 20,000 tons of structural steel. These towers had to be erected over the existing Bastille Bridge. All erected at night, sometimes during the weekend over bridge closures. We had over 120,000 bolts from a diameter from 5/8 all the way up to 1 1/4. You name a length, we had it. On this job, all of the bridge was actually detailed in Tekla, which is a steel building information modeling software. And this was really key for us because we were able to identify bolts, create assemblies, verify weights and centers of gravity of a lot of the pieces, and then push that downstream into a database that we used for erection and actually float-in planning. This right here is actually a screenshot from the 4D model that we did on the job. We took the steel model, took models that we made of the existing bridge, a lot of the existing conditions as well, generated that all into one conglomerated model that we used for planning of the float-in of the lift span. And just by doing that, we were able to vet out a couple conflicts that we wouldn't have seen otherwise. Something as simple as a piece of handrail that was on the lift span that would have conflicted with the tower. And had we not done all that work beforehand, we wouldn't have been able to see those, and we would have been in a very big time crunch. So anytime we have real time-sensitive work or something very critical in nature, having smart models, having conglomerated models, lots of the right information is really key for us. On a segmental bridge, we use them a lot, as you see here. Having an accurate geometry of the new bridges, existing bridges, if we're planning in this case, as you see here, some demo and erection, being able to verify that yes, our plan will work, we can fit the cranes in where we need to. We'll use those same models, say for in the case here, for false work designs, so that we can rapidly get out accurate geometry, accurate weights, dimensions to verify as a sort of a second check that our false work design is adequate, that we have the proper elevations, we have everything that we need to go ahead and build the work. We'll also use it for things just as simple as a simple sketch to show a concept, or for, in this case here, some very simple, seemingly straightforward bridge closure forms, which when the bridge is flat and not curved, everything works out really well, but when you have varying geometry, having models that allow you to coordinate all of your temporary works with that is really important. In the case here, this was a cast-in-place false work of a relatively straight portion of a bridge, but through the use of the model, we were actually able to generate quantities and, again, verify a lot of geometry that we wouldn't have been able to otherwise. The next job I'd like to briefly touch on here, this is actually a cast-in-place segmental bridge up in Brattleboro, Vermont. This particular job is a design build, and in design build, being able to quickly update a model with design changes is key, especially if us as contractors are taking ownership of the model during construction. Again, here this was a case where we went to 4D scheduling, actually not only to vet out our general process, but also, that you can see there as well, sort of to plan out our formwork and to make sure that, yes, one set of forms is enough, that we didn't need to purchase two. We even go so far as to include a lot of the ties, and in this case also rebar, because being able to, in a 4D environment, set the order that the rebar is going up and visualize that is really key for the folks out in the field who have to go and build this work. This is the pier table for that same job that we actually detailed out in 3D. Real key for us here, coordinating all of the embeds, all of the post-tensioning, making sure it was all going to fit before we went ahead and put anything actually in the field. Excuse me. Next job here, this is the I-4 connector down in Tampa, Florida. This was a very large segmental job, had over 2,600 different segments. And back then when we were creating the model for this particular job, we had to do things often the old way, which in this case involved a lot of custom scripts to generate the cross-sections that we would then align to segmental joint coordinates. And it was definitely not quick to update, and when you just have a static 3D model object, you really only get very generic properties on the objects. You're not getting a lot of intelligence, and you're not getting the best use out of that model that you really could. On Bonner Bridge, beautiful new job out in the Outer Banks of North Carolina. We are building a 2.8-mile segmental and traditional cast-in-place structure. On this job, we've gone through and we've made quite a number of bridge models for it, and I kind of wanted to dive in a little bit and show you how we used OBM to create some of these models and how it really sped up some of the work that would have taken us quite a bit of time otherwise. In the case of bridge data, this is a screenshot here actually inside of Open Bridge Modeler, just to kind of show you some of the organization and data that is available inside the model. Getting the alignment and everything in, because this was a design build, we simply got the alignment files directly from our design build partners. Pulling the information in is really straightforward, and updating that is really easy as well. I had actually initially selected a previous design iteration of the alignment, and it only took a couple minutes to update the model to that correct alignment. All the stationing and everything was maintained. Substructure on this job is definitely a challenge because the bridge is so long. We have allotted repeated elements, but we also have elements that have some slight variation to them. In the case of Open Bridge Modeler, the template system allows us to very quickly reuse an element configuration, and we have the ability to dive in and manipulate some individual elements as needed. This here is actually one of the approach substructure templates that we used. When we dive in a little bit further, we have a lot of control as far as pile spacing, embedment, and size that we can do to go ahead and manipulate those elements to get them to fit the design intent. Raul showed you a little bit earlier, and this is another example of just some of the different types of piers that you can actually generate straight out of the box. Really, there is practically no limit to what you can do. And here's an actual sample of one of the substructure vents on the Bonner Bridge, and you can actually see the cast-in-place pedestals and the bearings. If you note, there's actually varying pedestal elevations, So in OBM, based on how the bridge type is, I can go ahead and set the pier caps to either be sloped or flat, or adjust those to fit specific elevations depending on the need. Superstructure is really just as straightforward. Again, it all just starts with I'm generating the template type, which in this case we have a bunch of 96-inch precast girders on either of the approaches. I'm generating the data for each of the units. I can quickly copy over a lot of that reused data from unit to unit, so I'm not re-inputting a lot of the data that normally would have been kind of a tedious effort. Here it's a relatively straightforward copy and paste to generate, a bridge that's, nearly 3 miles long in a pretty quick period of time. And again, I can actually dive in now into the individual beams and manipulate them from there. Say in the case we have one span, or there's a couple particular units that may have something a little bit atypical about them that we need to go ahead and edit, and that's all very straightforward. On superstructure, this is a segmental portion in the center navigation spans. It all starts with the 2D line work. The great thing is that we can make a lot of parameters. We can vary those parameters very easily. So in terms of varying segment depth, varying thicknesses, it's all very straightforward to do. Some of the things we've actually even tested around a little bit is our own tendons inside, because when you have the general segment geometry, that gets you 90% of the way there. But it's a lot of those little details and add-ins that can really take the model to the next level. And for us, that could be, as seen here, having tendons, or things as simple as blisters or deviation blocks inside the tendons. In this case, we were actually there's what they call a point control. So I can actually have a line of geometry that's at sort of any elevation, and I can use that to control where these tendons are actually moving. So I can pretty quickly generate some tendon geometry just based off of some simple line work that follows the bridge alignment. Once I've taken that to the next level here, this is actually the completed superstructure of the bridge. So you can see here we do have a varying cross slope. We have a little bit of a super elevation. We have a varying depth. There's a varying segmental bottom slab thickness as well. And you can see inside here some of the data that's available, just by simply clicking on either one of the units or one of the segments. I'm quickly getting not only areas and cross-sections and some basic parameters, but things that are very important such as weight or concrete class, a lot of data that I can use very easily and push downstream. I mentioned before that there's really a lot you can do. I've kind of played around a bit too with some real wild curves and some really different geometry, and I've been able to do some pretty interesting stuff like seen here, which would never be a bridge in real life, but I mentioned before quantities. We can pretty quickly generate some quantity reports, which especially if we're in an estimate phase or we're in a very quick design iteration, I can very quickly spit out concrete quantities or weights. That's really a huge benefit for us rather than doing some sort of a manual takeoff. And based on the testing that we've done, it's very straightforward and easy to get that information out and to validate it and to trust that the information is correct. Now, getting the model data to the field. So it's great if we have a model and it's inside the computer in the office, but what can really make that model incredibly useful is if we are able to push that out into the field. So with, a simple publishing of an iModel, making it a mobile iModel, we can push that out and we can open up these models in OpenRoads and in Navigator on the iPad, and that's what you see here. And all the data remains intact on the segment there on the left. You can see we still have the volumes, we still have the weights, we have the segment properties. And on the right-hand side, you can see this is just a haunch segment for build-up on top of one of the beams. We maintain all of that data, so we're not re-inputting anything, and it's all maintained throughout the full life cycle from design into construction for us. So with that, I'd like to turn this over to Dennis, who's going to speak in detail a little bit more about the rebar. Dennis?
All right, thanks, Andre. My name is Dennis Fontenot. I'm with Commercial Metals. in the central region, which is located in Texas. And I'm going to give you a little information about 3D rebar detailing in the bridge world. Just to let you know is that in Texas, we don't detail the bridges, the engineers do, and it's a little bit different for us. Let's skip this slide. So we worked with Caltrans a few months ago on a little case study on a bridge that they have already built. And this Otay Mesa Road bridge here was already built. This is a model within a Google Earth image, and they inserted it. This is the model that Caltrans gave us. Looks pretty simple. Looking at it, not a problem for a detailer to reinforce this. Once we started looking at the model, we noticed that in the model, that the model was incomplete. It had a shell, that's fine, but there's still a lot of data that we need in order to reinforce. And whenever we're sharing models, the most important thing is that that model is complete if we're going to be reinforcing the model. And it was obvious that they didn't pull their 2D drawings from the model, because if they did, the information for the girders would have been in there. So we went ahead and we modeled the missing members, concrete members. As you can see, it's showing up in green. And one of the challenges that we had with this was that modeling the reinforcing with the B-splines was a challenge for the detailer just to keep the bars in line. We could have used face recognition, but we wanted to control the rebar. The bridge had a B-spline on the outer edges. It was at a skew, and it also sloped at the top, and it sloped across the deck. And what we did was we used guidelines, used quite a bit of guidelines to control all the rebar, which really helps. You can use these guidelines. The rebar will follow it in a spacing pattern or just in a straight edge. Other thing I want to point out is 3D model accuracy. So with the same model that we were testing, doing this case study with Caltrans, then we noticed that the retaining wall was modeled straight up. It was not matching the contract documents. So the rebar detailer modified the model to match the contract documents. At the beginning, if Caltrans and the general contractor decided that the wall would be poured straight up, that collaboration back down to the fabricator would have been done, and we would have changed the rebar or the model to match what the general contractor wants. So I asked my detailer, I said, what are some of the challenges that you see with modeling rebar for bridges? And he was pretty honest about it. Complete lack of square corners, straight edges. Whenever you're modeling, you can't use the traditional XY axis and the front, top, and side views to reinforce the concrete members. You have to spend a lot of time rotating yourself around, orientating yourself around the model so you can reinforce it properly. This is just an image where that you can use, isolate an abutment, pull out a section of it, where that you can do a presentation to your placers, to your engineers, if there is any type of constructability issue. This does help. This visual aid here helps out a lot from a detailer to contractor to placer and even to the engineers. And this is just a little fly through. Of that same bridge. So this is other things you can do with a model to do a presentation to show the rebar All right, so that was just a short presentation on a fly-through of the bridge. Other items we can get out of the model is the 2D placing drawings that are created here. These come out of the model. And also to get the bar list whenever we're releasing it for production. So this is one release right here that you see. And also to get all the weights for the different members broke down by the concrete members. IFC Viewer. Industry Foundation Class is what IFC stands for. And whenever you output an IFC of a rebar model, the properties of the rebar, I'm selecting a group of bars here. The properties of the rebar are also in that IFC. It carries with it. And I'm showing another one so you can see how it selects a larger group of bars. If you can see the green bars that are selected, same thing. You can get the properties out of it. Now, the Bentley iPad Navigator, which Andre mentioned earlier, we use as well. And we create an I model, and an I model is like a container. So you can have a model and its documents associated with that model. So for this bridge, we have all our section cuts that are showing up in this model. We can select any one of those and view it. We also have our documents. So we have contract documents, we have the bar list in there, and we also have some placing drawings. So as we click on those tabs, the items come up. This will be very helpful when you're out in the field and you're reviewing the rebar. It could be helpful for your placers to navigate to it. Being able to navigate through the model and look at, like in this case right here, where we're walking through one of the abutments. Able to select the bars, same group of bars I selected earlier in the IFC, and getting the same properties of the bar. Another project I wanted to talk about, now this is a live project, this isn't a case study. This is the Gerald Desmond Bridge in Long Beach, California. We are working with our group in Etowanda, California. CMC is currently fabricating all the rebar in this job, as well as placing the rebar. And the two areas that we're focused on is the two column towers. So we're taking this from the 399 to the 515 elevation that is around the anchor, cable anchor boxes. And this project is about 24,000 tons of rebar. We have fabricated about 13,000 tons. We have fabricated in place 13,000 tons of rebar. This is the foundation, so you can see the size of the base of these columns. So we took on and started modeling the concrete, and as you see, the different colors means the different lifts. I've isolated one of the lifts, and just to kind of show you where the anchor boxes 5 and 6 are. And you'll see this also cut later in this presentation that it's all reinforced. We also were able to obtain an IFC file from Stinger Bridge and Iron. Their model we took and referenced into our concrete model. So the structural steel, when we brought it into the concrete model, it fit like a glove. So that tells you that the structural steel is per the contract documents, and the concrete was too. Here's a couple of details of what the rebar looks like when it's laid in to those walls. And I also want to talk about a little before we get into the other details is your naming conventions. Of whenever you're modeling, it's important that you have a consistency in your labeling of your levels so that whenever you're navigating in your model, you can turn on or off. Plus, this information also carries into an IFC, carries into an iModel, also into a PDF. So you can get a 3D PDF out here and able to turn on or off these levels. So the more organized you are with your level naming convention, the easier it is to use outside the model. So here's that one little area I was talking to you about that's going to be reinforced later. So this, you can see the rebar that's coming up at the very top. It has HRC couplers. You can see in the plan section, you can see the little ties added in there, also the structural steel. So I dropped the concrete level on this, and I zoomed in just on the rebar, selected a few bars, and you can see where, like the number 11 bars there, it has 4 number 11s grouped in that one group there. Grade 6E epoxy on the size. You have the bar mark, 11A 136, and then the spacing, and also what the level is within the model. Same thing with the ties to the right. Here's what the rebar looks like. This is the first lift, but going up this tower, it's going to look similar. And all this rebar is epoxy coated with purple epoxy. You can see the HRC couplers in the smaller view there. It's shrink wrap to protect the couplers from rust. And you also see where all those little J-hook ties, it's 100%. Every intersection is tied up. In the section that we're modeling above, where the anchor box is, it's 50%. It's not 100% tied up like that. So here's one of the more difficult anchor boxes that we had. It had like a corbel, and it comes into the center of the towers. And if you were doing this in 2D, you'll have some challenges looking at the constructability issues, the fabrication issues that you would have. And this is what my detailer, the 3D BIM rebar detailer, when he's looking at everything, this is what his desk looks like. So he has multiple views up. He has his PDF. So he's working with 3 different screens and probably about 6 different views there. That one section there, I isolated out, and I took out the ties for more clarity. And you can see how these views can be very powerful and more visual aid for the guys in the field. I also took that same section and isolated the concrete just with those corbels and drilled into just one of the corbels, so I can look at the rebar. So I'm selecting the spiral that's going around that pipe. So the same thing with the IFC viewer. In this model here, we had terminators, so HRC terminators on the end of the bars. And we also had HRC couplers. And if you see the information that carries with those couplers, you have the manufacturer, you also have the website. So you can actually link out to the website and look at the specifications of those couplers. So same thing with the rebar. showed earlier, the properties of the bar and the bending properties. And then our guys in the field using their iPads to view the model. Navigating in, you can turn off your different levels, drill down into the model, and look at different areas and get a good visual of how the rebar is going to be placed. So that's the end of my presentation. Bob, I'll pass it on to you.
All right. Thanks, Dennis. Well, that's a great presentation from Raul, Andre, and Dennis, showing from their various perspectives how integrated technology and processes can optimize bridge design and construction, reducing costs, shortening schedules, and minimizing rework. So for the next few minutes, in some of the time we have left, our three presenters will be responding to some of the questions that were submitted during the presentation. And you can continue to submit questions using the Ask a Question box on the left side of the webcast dashboard. So first question we have, when a BRIM model is turned over to a contractor, does the contractor typically have to verify the accuracy and take ownership of the model? If not, is that a potential claim avenue?
Well, I'll go ahead and take a stab at that. So it's actually very rare for us to get a model turned over. Normally, we end up recreating all of the 2D plans in 3D, especially on the bridge and infrastructure side. It's a little bit different from a commercial avenue. Generally, that's the case of where it's written into the contract that we are receiving the model from the engineer. And it all depends on the contract. If there is going to be any sort of a model turnover, we do have a pretty detailed validation process where, depending on what the use is for the model, we're going to go through and check certain key dimensions, check a lot of the parameters, make sure that things make sense before we go ahead and trust that. And I think a lot of that comes down to, right now, the owners and what they require and what their requirements are at the end of the day and how they set up the contract.
All right. I've got a question for Dennis. What's the approximate time it took to model the single span for a box girder bridge?
For that box girder bridge, and also you got to understand, we had to fix a lot of the concrete. So with the modeling and the reinforcement, I think just reinforcement, it probably took about 40 to 60 hours to complete. And that is creating the 2D drawings as well.
Next question. In Open Bridge Modeler, can you create custom abutments with wing walls?
It's not available at the time, but this is Raul. You can create really intricate abutments, including the wing walls. The nicest thing is that you can place them in a DGN lead. An Open Bridge Modeler, we're able to look at them and place them in the correct station and offset and elevation, okay?
And here's a question. I can't recall if this was during Andre's or Dennis's presentation about how did you get the wing walls? Andre, is it?
Dennis, you can probably speak to that and how you did that at Otay Mesa.
Oh, on the retaining walls on the bridge?
Yes.
Okay, so the retaining walls on the bridge, we got the original model from Caltrans. Then we also had their 2D contract documents. So knowing what the wall, the height, and the backfill and that type of stuff, they had a schedule for the retaining walls. So we took it straight off of their structural contract drawings, and we created the correct retaining wall in the model and reinforced it.
Dennis, another question for you. Can the program generate the 2D sheets showing the rebar?
Yes, it can. Now, what I'm using is Pro Concrete, and yes, you can create 2D drawings out of it. That's what I showed in my presentation.
All right. Well, that's all the time we're going to take for questions today. Some of
Bob, 1 second. I just wanted to also add to Dennis that particular model, and that it was used for the rebar placement was created with OpenBridge Modeler.
All right. So as it says on the slide, that there will be questions that have not been that were submitted, but we didn't take time to answer today, will be available online within a few days at the web address shown on the slide. So please check there for further discussion about today's topic. Also, to download your certificate of completion, that's under the Event Resources section on the left side of the screen. So after downloading the certificate, you can enter your name in it and print and save a copy of the PDF. The certificate will be available through the end of today only, and a hard copy will not be mailed or emailed to you. If you missed our note at the beginning and you are watching the live webcast with a group on one person's computer, please download the multiple viewer registration form and complete and submit the form to receive credit. We need this information in case you are audited and we are contacted to verify this continuing education activity. Additionally, this webcast is being recorded, or was recorded, and will be archived on csengineermag.com/continuing education. For viewers of archived webcasts, click on the quiz button at the bottom of your screen to take a quiz on the presentation. Archive viewers must pass a quiz in order to download a certificate of completion. So as we conclude, you should see a webcast evaluation survey, and we appreciate your feedback, which helps WAG Group and sponsors such as Bentley plan future webcasts. So thank you to Raul, Andre, and Dennis, and to everyone who joined us. This ends today's webcast.